So section 1 in chapter 7 just talks a little bit about ions and how ions form compounds. So ionic compounds are not technically molecules. You do not have a molecule of sodium chloride where sodium is bound to a chlorine and this is the unit of sodium chloride. That doesn't really exist that way. Instead, the reason why we write the formula for sodium chloride as NaCl is because in the lattice of the ionic compound, the ratio of sodium to chlorine is 1:1. So we have 1 sodium for every 1 chlorine. We mentioned in a previous chapter that for ionic compounds, the empirical formula is the same as the compound formula. However, for an ionic compound, you shouldn't really call it a molecular formula because there's not really a molecule. But the formula for an ionic compound is the empirical formula. It's the simplest ratio of elements that you have in the compound. So in contrast, magnesium chloride, again, we don't have a magnesium chloride molecule that looks like this. We have a collection of magnesium ions and chloride ions, and since magnesium is +2 and chloride is -1, they occur in a 1:2 ratio. So here is a diagram in your textbook of what the sodium chloride crystal looks like when it's solid. So again, you'll notice that it's not just a sodium and a chlorine linked together as a molecule. That is not what it is like. If we look at this sodium ion, it's surrounded on 6 sides by chloride ions, and then each chloride ion is surrounded on 6 sides by sodium ions. So the positive and negative ions are alternating, both, back and forth, left to right they're alternating, up and down they're alternating. We have negative, positive, negative, negative, positive, negative. So each of these 3 dimensions sees alternating positive and negative charges so that they are attracted to the maximum amount of negative charges surrounding them. And overall, there's a 1:1 ratio of sodium +1 to chloride -1. So this is what it looks like as a solid. Here I have drawn the picture of a water molecule. We have oxygen with 2 hydrogens actually stuck to it. This is 1 water molecule. It does exist as 2 hydrogens for every 1 oxygen, and they are bound together with covalent bonds. It's a bent shape. We'll be looking a little bit more at that very shortly. And the oxygen end of the molecule has more electron density. This little delta means that there's a slightly negative charge at this end, not a full charge, but this end is more negative, and this end of the molecule is more positive because there's less electron density here. The electrons spend most of their time on this end of the molecule. And so that makes water very good for dissolving most ionic compounds. Here I have a little bit of a diagram of what happens when sodium chloride dissolves in water. The sodium ions, instead of being next to the chloride ions, are now surrounded by water molecules, and the negative ends of the water molecules are pointed in towards the positive sodium ion. For the chloride ion, again, this is surrounded by water molecules, and the positive ends of the water molecules are pointed towards the chloride ion there. And the negative ends here pointed toward this sodium. So they do separate, they dissociate in water. That makes a salt water solution a very good conductor of electricity. Salt ionic compounds can be called strong electrolytes because they completely dissociate, and the water is now full of charged ions, and so it conducts electricity fairly well. I did find a colorful picture in your textbook of a similar process, ionic compounds being dissolved in water. This is potassium chloride instead of sodium chloride, but it's a similar thought. This is a topic talked about in chapter 11 of your textbook, which we are not covering this semester. It's what you will be getting into in Chemistry 102. So if you want to look ahead at this diagram, that is figure 11.7 in your textbook in chapter 11. Also, this is what I was mentioning about these ionic compounds. When they dissolve in water, since there are charges in the water, it makes this saltwater solution a very good conductor of electricity. Molecules that do not dissociate, covalent molecules dissolved in water, such as ethanol or even glucose, these do not dissociate when you dissolve them in water, and so solutions of ethanol or methanol or glucose would not conduct electricity very well. Weak electrolytes are weak acids and bases that partially ionize. So here we have acetic acid, some of it is molecules, a very, very small percentage is ions, and so you have this dimly lit light bulb as evidence that it is weakly conducting electricity. So again, that is a topic that you will revisit next semester. The only other thing that they mention in section 1 of chapter 7 is the electron configuration for an ion, as opposed to just the element. So the element sodium has 11 electrons. A sodium ion would have 10 electrons. And so it would have the electron configuration 1s2, 2s2, 2p6, which is the same electron configuration as neon, one of the noble gases. So that extra stable configuration is why sodium likes to form a +1 ion rather than other charges. The chloride ion has 18 electrons. Chlorine has 17 with a -1 charge. There are 18 electrons. Again, because it gives that the same electron configuration as a noble gas, argon. It has a complete outer shell. This time the outer shell is in the level 3. So chromium ion, again, that's a transition metal ion, so we have to be a little bit careful. The chromium is going to lose the 4s first before it loses the 3d. Also, coincidentally, chromium is one of those exceptions that we didn't focus too much on. If you didn't remember that chromium was an exception, you would still get the same answer for the chromium 3 ion. And that is 1s2, 2s2, 2p6, 3s2, 3p6, and 3d3. The same as argon with just a couple of d electrons. And these superscripts add up to 21. There are 21 electrons in the chromium 3 ion. So for selenium, there are 36 electrons. For the selenium ion, there are 36 electrons. Selenium has 34. And that gives it the same electron configuration as krypton, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6.